Welcome back. Today we're going to talk about solving a system of linear equations, and we're going to use the method of graphing to do that. Okay, so let's do a quick review about how to graph lines because we're going to rely on this skill very heavily during this lesson. So if we were asked to graph the line y is equals to 2x plus 1, I want you to recall that this is the y-intercept. So what I'm going to do is I'm going to find 1 on the y-axis, and then I'm going to use the slope, which is 2 over 1, to show rise. So it's going to be up 2, which is a rise of 2, and a horizontal change of positive 1, so right 1. So up 1, 2, and right 1, up 1, 2, and right 1. Likewise, I can go down 2 and left 1, down 2 and left 1. Okay, down 2 and left 1 right here. So all of these points are collinear. We join them with a straight line like this, and we make the line as long as possible like this. And we put arrowheads on the line, and there we have graphed the line. So I want you to also recall that a solution to an equation is a point. So first of all, any point that we just found is a solution to the equation, meaning that I could take the coordinates of this point, like this is 1, 1, 2, 3, and I can substitute the value of 1 in for x, so 2 times 1 plus 1, and put 3 in for y, and this becomes a true statement, that 3 is equal to 2 times 1 plus 1. That is true. 2 times 1 is 2 plus 1 is 3. Okay, so an xy coordinate on the line is a solution to the equation, and I can tell that it's a solution because when I substitute the x in for x of the variable x in the equation and the y in for the y in the equation, it becomes a true statement. Okay. So today we're going to be talking about something called a system of equations. And a system of equations is a set of equations that have the same variables rather. And so we're going to be mostly looking at systems that are only have 2 equations here, but you can have systems with any number of equations, but we're going to focus on the ones with only 2 equations like we see. Okay, and you'll see in this system, these equations taken together are called a system because there's 2 of them, or there's more than one, okay? And they have the same variables, x and y are both raised to the first power. So an ordered pair is a solution of a system of equations if it is a solution to every system in the set. So I am looking for a solution to the system. So I'm looking for an xy coordinate such that it is a solution to the first equation and it's a solution to the second equation. Well, one way of doing this is by using the method of graphing. So if I were to graph these 2 equations here, so first of all, this first equation, I have a y-intercept of -2 and a slope of 3. So I can go up 1, 2, 3 and across 1, up 1, 2, 3 and across 1. I can go down 1, 2, 3, 1, 2, 3 and over 1. Okay, so I'm going to go ahead and graph this. Okay, and I'm going to put my arrowheads on. So that's my first equation right here. And I'm going to graph my second equation as well. So I have a y-intercept of +3. So I'm going to go up 1, 2, 3. And then my rise over run is -2 over 1. So I drop down 1, 2, and I go right 1. And I go down 1, 2, 1, 2, and right 1, 1, 2, 1. And actually, this is going to be enough, as many points as I need. So I'll draw this line right through these points, make it as long as possible. And I can already see that these 2 lines cross, that they intersect. And I'm going to put the arrowheads on my line. So these 2 lines, so imagine these 2 lines are actually, remember that each line is the set of all solutions to each equation, right? So every single point on the line, these little purple points, these are all solutions to this second equation, right? Those are solutions to the second equation. Whereas if I look at the line where I started that was green, all of these points on this line, all these tiny little points, these are solutions to this equation. Well, this intersection point right here, this is 1, 1. This is a point that's shared by both of the lines. Well, geometrically, it means that that's where the lines intersect. But algebraically, it means that this point that's shared by 2 lines, this point is a solution to the green equation, and it's also a solution to the purple equation. Well, that means that algebraically, it's a solution to both of the equations. So that means I can put the point 1, 1 into both of the equations and it would arrive at a true statement. So let's go ahead and try that. So 1 should be equal to 3 times 1 minus 2. 1 is equal to 3 minus 2, so 1 is equal to 1. So it's definitely a solution to the first equation here. Let's try the second equation. 1 is equal to negative 2 times 1 plus 3. 1 is equal to negative 2 plus 3, and 1 is equal to 1. So that's also a solution to the second equation, so this being the second equation. So what we say is that since these equations are taken together as a system, we say that 1, 1 is 1 comma 1, this coordinate is a solution to the system of equations, right? Whereas there's infinitely many solutions to each equation when they're taken by themselves, taken together as a system, there's only one solution, and it's this coordinate 1, 1. Right? Because it's a solution to both of them. What does it look like geometrically? Well, it looks like there's a point where the two lines intersect. There's exactly one point where they intersect. Algebraically, I can put this point back in and they both arrive at true statements. I know there's only one because if I look at them geometrically, they only cross once. Okay, so when we say we solve, so if we have a system, sometimes they're called a system of simultaneous equations. When we solve a system like this, we are looking for a point or points that are solutions to both equations. And what that looks like is it looks like a point where both of the lines intersect. We're going to have other methods of solving systems of equations, but this is the geometric method or the graphing method that we're going to use to solve. Okay, there's three things that can happen when two lines are drawn on the same graph. Situation number one is that there's one solution. So this looks like the lines only intersecting once. This is a system of equations that only has one solution. Okay. Now, situation number two, you could actually have lines that are drawn parallel, which means parallel lines never cross, right? They always maintain the same distance away from each other. They never cross. So this is a system of equations with no solutions. Okay. And we looked at this in the last module when we talked about equations. When you set them equal to each other, there are some equations that have no solutions. Well, that looks like equations that have the same coefficient for x, right? If they have the same slope, like y is equal to 3x plus 1 and y is equal to 3x plus 2, well, they have different y-intercepts, but they have the same slope. That means that they meet the y-axis at different places, but their slope is the same, so it means that they're parallel, and there's going to be no solutions to this system of equations. And we saw that in the last module when we had an equation when we tried to set them equal to each other, and there's nothing here there's no x that I can put in here such that when I multiply it by 3 and add 1, it's the same as when I multiply it by 3 and add 2. That's just not going to happen, because if I tried to solve this and I subtracted 3x from both sides, I get 1 is equal to 2, right? And that's not a true statement. Now, these particular lines that were drawn, you can actually, I came up with this example here, but we can actually see the slope here is, let's see, rise up 2 over 1. So they both have this equation right here is y is equal to 2x plus 1, and this is y is equal to 2x plus 2. So they both have the same slope, but different y-intercepts, so they'll never meet. Okay, in this situation, we'd say that the system has no solutions. Each equation has solutions, but the system doesn't have a solution. Okay, the other situation is, and we saw this before, is that when you graph two lines, they could actually just be the same line, right? So the reason why this is a little darker than, you might not be able to perceive this with your eyes, but this line is a little darker than the other ones is because I actually graphed two equations right on top of each other. And we saw this situation before, so if you had like 3 times x plus 1, and we're trying to solve this equation right here, well, what happens is they arrive at the true statement that 0 is equal to 0, and we know equations like this have infinitely many solutions. So lines that are graphed and they're the same exact line, that system has infinitely many solutions because they meet at every single point on their respective lines, because every point on one line is also a point on the other line. Okay, so these are three different situations that can happen when you have a system of equations. You could have one solution, you could have no solutions, and you could have infinitely many solutions. Notice you can't have a system of linear equations that have two solutions, for instance. You can't have a system that has 3 solutions. That's not going to work out because there's no way two lines are going to meet each other exactly 3 times or exactly twice. They'd have to be some sort of curve in a line or something. Okay, but two lines can't do that. They either meet once, no time, or infinitely many times. Okay, now let's try to solve a system of equations that's given in standard. So if it's given in standard form, which means that it's not solved for y, the first thing we're going to have to do is actually solve it for y. So this first equation right here, what I want to do is I want to get y, I want to isolate y. So I want to subtract 2x from both sides. Okay, so I have 2y is equal to 4 minus 2x. Okay, and then I want to have 2x, I want to use KCC to put the negative 2x, I want to put it to the left right here. So I have negative 2x plus 4. And finally, I want to divide each side by 2 because I want the coefficient of y to be 1. So I have y is equal to, now I'm going to divide them, so it's negative 2x divided by 2 plus 4 divided by 2. So I really have y is equal to negative 1x plus 2, okay? So I have a y-intercept of 2 and a slope of negative 1. Okay, so whoops. Here's my line right here. In the interest of time, I'm just going to leave out the arrowheads for a minute, okay? And then the next one, I have x plus y equals 2. Well, all I have to do here is subtract the x. And what I'm going to do is I'm going to just rewrite this as negative x plus 2. So that my y-intercept is 2 and my slope is, wait a minute, my slope is negative 1. So, indeed, look at what I have. These are both the same equation, right? So the green line is on the same as the purple equation that we started with here. So it means that every single tiny little point on this line is a solution to this equation. So what I would say is that this system of equations has infinitely many solutions. So 2 skills we learned here. We learned how to transition from an equation in this form to an equation in slope-intercept form. And we learned that when they're the exact same equation and we go to graph them, that the system is going to have infinitely many solutions. And that is the end of the lesson for today.